Good evening. Today I'll be discussing about. I'm Calvin Joseph, and today I'll be conducting the problem solving and doubt clearing session for this course. And this week is predominantly about. It is all about a microcontroller. So I'll be talking about the STM32 microcontroller and the C2000 microcontroller. Also, we'll be discussing about, and we'll also be touching upon the various peripherals which are available in the microcontroller and how we can use those peripherals and how do they fit in with the thing which we want to perform. Like we want to learn digital control. How will we use our microcontroller as a tool, as a to implement digital control? We look into that. Also, there are certain reference designs and certain hardware converters also were demonstrated. So I'll be briefly touching upon that. Okay. Okay, so now we will start with the STM32 microcontroller. So the STM32 microcontroller is it is a very popular microcontroller which has been there in the market for quite a long time, and it is very handy. It has a large number of peripherals which we can use for running our digital control. So, for example, let us consider this to be our microcontroller. You guys are able to see my pointer, right?
Yes.
Yes. So like this entire block is like our microcontroller is over here. Okay. And so it has all various features. It has ADC, it has a DAC, it has comparators, it has op-amps, it has timers. Okay, so all of these peripherals which we require in an FPGA. So the difference between the microcontroller and the FPGA is in the microcontroller, all these peripherals are present inside the microcontroller. But if you are using an FPGA, like the one which sir has been using it, and like we discussed about how you require an ADC driver, you require a DAC driver, you require an ADC, you require a DAC, then the ADC data has to be sent to like the ADC requires a clock coming from the FPGA to trigger the ADC, and the ADC's output has to be sent to the FPGA. So those complications are there. So they are external. So you have a FPGA also, which is a very large block. It takes up a lot of space, and then you have, and in addition to that, you have the ADC driver external stuff. So it is taking up a lot of space. But the advantage with the microcontroller is you have the ADC internal. Okay, you can see, like you have the ADC over here, you have timers over here. Okay, so like that, you have various features are available for you to use, and so you just have to basically power on the microcontroller, and you have to dump a code. And in the Nucleo code, there's a debugger which facilitates dumping the code from the computer into the microcontroller, and then the microcontroller has the code and it can run. Okay, and see, like we also require comparators. In for implementing current mode control, we require a comparator. Also, you might require op-amps, etc. So all these are internally available in the microcontroller. And okay. Also, there are various SPI protocols, like various serial communication protocols also are there, like the CAN bus protocol, the SPI protocol, UART protocol, etc. So these are also can be used for communicating information. So I'll proceed. So first about the STM32 microcontroller. It is a 32-bit microcontroller, just based on the ARM processor. And in the microcontroller which we are using, it has a 170 megahertz clock. The clock can reach as high as 170 megahertz. And the various peripherals also are there, just timers, ADCs, DACs, comparators, etc. Now, when we want to make the STM32 code, okay, the STM32 CubeMX code, like we use the STM32 CubeMX software. So what does this software do? It is like a graphical user interface tool. It has the pins of the microcontroller. What do we do is we go and configure the peripherals. Like we go and configure the settings of the ADC. we configure the settings of the timer which we want to use, so we configure the setting of the DAC, etc. So what we do, we first select which microcontroller we want, which board we have. Once we select the microcontroller, then we go and configure the peripherals, we configure the clock and other things. And then after we have configured it, then we generate the initial C code. So to generate the initialization code, and so it saves our time. We don't need to manually write all the initialization C code, etc. It will be generated automatically by this CubeMX software. Once this STM32 CubeMX has initialized and it has generated that code, then we will use a IR embedded workbench. So this is an IR embedded workbench, and this is the code which comes out from which is generated. Okay, so in this code we have to write our various functions, our various lines of code and logic, etc. We have to write in this integrated developer environment, and after we write it, then we can run the code and we can also debug the code, etc. So actually, they have showed the steps. Someone is saying something.
Sir, this is 32-bit. We are saying STM30 is a 32-bit method.
Yes, yes.
Sir, in that which it means that it can perform digital operations on 32-bit data. Is that it means, sir?
See,
the last bit value, place value is 2 to the power 32.
Yeah,
the MSB.
No. Yes, the MSB is 32 bits. Basically, it is about the size of the registers in the microcontroller. Okay. See, there might be a possibility of even doing higher, what do you say? Higher values, also computation, etc. might be a possibility. I don't know about that. But what I remember is like the registers of the microcontrollers, the registers maximum size is 32 bit.
Sir, if we put...
You said something?
No, sir, it is actually, it can handle data from 0 to 4.29 10 to the power 9. Is that it mean? Because 2 power 32 is 4.294 10 to the power 9.
I'll have to look into that actually. That I'm not very exactly sure. You could define those values because I haven't worked using such high values, so I can comment on that.
No, I'm just saying.
Yes. You could use such high values, but then you have to take care of overflow, underflow. Those things you might have to keep that into consideration in your logic. Like that. If you want to
sir,
use
just trying to
no,
I'm not asking in a way that I was using it. But just trying to understand that because in digital circuit, digital control, we always deal with that 4 bits, that 8421.
Yeah.
In digital logic, 1002 111. But here, if it's 32 bit means it goes from 32 zeros to something higher value.
Yeah. Yeah. So this is a range which is possible for it to go, but when you're working at those high ranges, you have to be careful. Okay. So this they had shown how to download STM32 CubeMX, etc. So now how to download this IR embedded workbench. Okay. So for this IR embedded workbench, you have to, these are the steps written over here, which you can follow. And you have to click on try for free and you have to use the code size limited one. Okay, you have to use the code size limited option. And you have to enter your details over here. And once you enter the details, you'll have to register and you will get a license and a link to download to your email. And you must use that license. So then you must download the IR embedded workbench software. And after downloading that, you must enter the license details which have been provided to you, and you can run the IR embedded workbench for compiling and debugging your code. Okay. So these are the steps. Now, this is the board. This is a Nucleo G474RE board, which has been used. So this is the microcontroller. Okay. This is the 64-pin microcontroller, which is that 32-bit microcontroller. And this is your Nucleo board. It has a debugger, etc. This is for your power comes from here, from the USB. And from via the USB also, you are also transferring data. Okay, you're also transferring data to dump the code. And that is dumped via this IC into this microcontroller. And these, see, you see there's a CN7 written here and there's a CN10 written over here. So what happens is the microcontroller has 64 pins, all right? So those pins come over here to one pin, to another connector pin, etc. Those pins come. Those pins are configured, and for that, to know which pin of the microcontroller is configured to which connector, that you'll have to refer to the user manual. Okay, so these are known as your morpho pin header connectors. So this is like the male connectors, and when you want to connect this pin to your application, etc., you'll have to use a female connector to interface it. All right. And so there's CN7, CN10. Okay, these are your morpho pin header connectors, male connectors, and various pins are connected to various pins of the microcontroller. And there's these connectors. Okay, these connectors are known as CN8, CN6, CN5, CN9, etc. So these connectors are used for interfacing with the Arduino. So you can also use an Arduino board on top of this STM32 board. And this flexibility and this provision has been provided by ST Microelectronics. Further, there's a blue button, which is a user button. So if I click this button, then it is interfaced to one of the pins of the microcontroller, and it will generate an interrupt or something. And there I can write some events that if the button is pushed once, then you must change the frequency. Or if the button is pushed 3 times in 1 second, that means you have to stop the PWM signal, etc. Like that, we can configure it and we can define certain events based on the push button. Similarly, there's a reset button. So when I reset button, it starts again from the initial line of code. It's like basically restarting your computer when you restart. Similarly, this is like basically restarting your microcontroller. And okay. So any doubts in this?
Sir?
Yes.
This CN5 is basically connector, right? The CN5 and CN6, CN7.
Yeah, they're connectors. Yes.
Sir, what that number says as, does it the cross section of this pin, header pin? So can't we connect, suppose we are having a female connector of a CN6, can't we connect in CN7?
No, actually, these connectors were for interface, just connecting an Arduino on top of it. And so like when you connect an Arduino to it, suppose you connect it over here, okay? One of the Arduino's pins gets connected over here. So this is connected internally to the microcontroller some way. It is routed internally. It is not visible for you. Okay. Is that your doubt or what?
No, sir. Yeah, that's okay, sir. But here this CN7 they are saying.
Yes, it is just some basic number.
CN7. Okay. No, that I want to know whether that number represents the cross section of the pin.
Cross section of the pin. No. That size of the pin, that diameter of the pin you're asking.
Yeah, yes.
No, not about that.
Yes.
Not that. This, I think, if I'm not wrong,
all are of same size.
Yeah, I think it is 2.5 for mm1, I think. So the male one at least, I think. Okay. So the standard these jumper wires, jumper
dimension.
Cables, they are fitting it. Okay.
Okay.
Okay. So this is the microcontroller, and if you see, it is like just a small chip. So this Nucleo board is just for our, it is a basic board where we can use to test our levels of code. But when you have a particular application or a product, then what you do is you just have this small microcontroller chip. Okay, you just have this small microcontroller chip, and you attach this microcontroller chip IC in your PCB, and you route it accordingly, etc., and provide power. So that's why this entire space is not required. Then you just have a small microcontroller. So this additional space extra is just for our testing for us to do. But when in an actual product, after they have tested the code, tested the logic, tested the algorithm, etc., then they just put the small microcontroller chip. All right. And if you have, so that's how the microcontroller is so compact, and it has all the peripherals internal to it. Next, we'll start with the high resolution timer. So why do we use a timer? The timer is being used to generate a PWM signal. So just consider this. Okay. So this is like, if you remember, we studied counter based PWM signal. How will we generate a counter based PWM signal? So what happens is, this is my counter. It is initially 0, 1, 2, 3, 4, 5, etc. And it is being incremented. This is my after T clock. After each T clock, you get a clock signal, and the counter gets incremented. And this is the maximum value. Let us say over here, the maximum value is 11. Okay, over here, the maximum value is 11. So it reaches this maximum value. Once it reaches the maximum value, it gets reset and again starts from 0. Okay, now how much time it is on? When is it on? When this compare value, this red one is the compare value. When this compare value is greater than the counter value, then my switch is on. Okay, this is the normal PWM logic. Right. So in this case, if you see this case, what is your duty cycle? Your duty cycle is how much of time it is on. Okay, that is 7 upon 11. Okay, so based on this, based on your compare one value upon your final value, we can get the duty cycle. So this is basically a register. So these values are stored in a register. So if I change compare one, what do I change? I change the duty ratio. Okay, the duty ratio. And if I change the TBPRD register, I'm changing the frequency. I'm changing the frequency of my PWM. So if you look here, this TBPRD over here is 11. Okay, my TBPRD is 11. Assume my F clock was, say, let us take this figure for simplicity, 11 megahertz. All right. So this comes at a frequency of 11 megahertz. And after a total of 11 such clocks, it is again reset. So my frequency, my PWM frequency is F clock upon TBPRD. So that will be 11 megahertz divided by 11. So it will become 1 megahertz. All right. So first, what do we have to do is we have to select this clock. Okay, this counter clock. This clock frequency we selected. Okay, once this has been selected, then we have to assign values for TBPRD and compare one values. All right. In this case, I've shown the compare one value changing because when we are actually doing closed loop, the compare one values will change. But when we do open loop, we will set compare one value to be constant. Okay, it will be a constant thing. So if compare one value is constant, my TBPRD also is constant, then what I will get? I will get a fixed duty cycle. Fixed duty cycle with a fixed switching frequency. Okay. Okay. So any doubts in this? Sorry.
Sir,
Yes.
sir, here when in the first cycle, in the first gate pulse queue,
Mm-hmm.
the first on-off cycle,
Mm-hmm.
sir, when the compare waveform and the TPPRD are overlapping,
Mm-hmm. Okay,
before
okay,
that
okay.
itself the queue is
Achha.
finishing here.
Mm.
Whereas the next cycle it is
Okay, here I think there's a mistake. This has to stop over here. This is wrong. Hmm. This actually I overlooked. Okay.
so here we are actually updating the registers with the register TPPRD and CMP with the value.
Yeah, yeah, yeah. Hmm. We, yes. So there are certain registers of the timer. Okay. In those one register is for the time period, another register is for the compare value. Okay, for compare event value. So when we set those particular values and we configure the high resolution timer accordingly, then we can get that this output. Okay, I will also show how to do that. But this is just for the understanding of what actually is happening. Hmm. Then, so this TBPRD, I am setting, we have found like FPWM is F block upon TBPRD. So TBPRD is F block upon FPWM. Similarly, my duty, how much is my duty is compare one by TBPRD. Right. So next, also we will also have to introduce a certain dead time. Dead time also has to be introduced. That we will see in the code. Okay, so now I will show how to demonstrate this PWM and how we, we can use these PWM signals for open loop testing. So one thing to keep in mind is you must, when you make suppose you make a converter, okay, a buck converter you make, immediately you must not start closed loop. Okay, you must not start with closed loop immediately. You must do open loop first. You must check it in open loop. You must check it at 30% duty ratio, how much I'm getting, 50% duty ratio, how much I'm getting. You must vary the input voltage, you must vary. Okay, you must vary the load connected, you must change it. Okay, you can change it, increase it, etc. So you have to test it. In open loop, is it working as a buck converter should work? Is there any issue? Is the gate driver working? Is the other switches working? Are they able to handle that current? Once you have tested your converter, that first like you're testing whether the board which you have made is correct. Okay, whether it is properly routed, right? Whether there is any whether it is able to withstand the current, the voltages, etc. So that's why you first you have to test the board with open loop PWM signals. You have to check whether the open loop PWM signals are which are fed to your gate driver, and your gate driver is able to turn on the MOSFETs. You have to check whether you have given the appropriate dead time has been provided, and whether the converter is operating as it should operate with that particular fixed duty ratio. All right, there will be some deviation in the terms of the output voltage with respect to input voltage because of the parasitics of the buck converter. But overall, if you're increasing the input voltage, is the output voltage increasing, etc. So those basic things you have to check. Right. So for that, you have to generate PWM signals of fixed frequency, fixed duty ratio. Okay, once you have checked it for one frequency, then you can increase the frequency and check for another frequency, etc. But first you have to do open loop. So now I will show how we can generate open loop signals. So my screen is visible, right?
Yes, sir.
So, so for that, we have to use your STM32 CubeMX software. All right. Hold on, it will take some time. So have any of you used a microcontroller or are using currently?
Yes.
Okay. You're using TI, right?
Yeah, C2000.
Okay. So this is my STM32 CubeMX. This was already demonstrated, but I'll also show. So I'm going to create a new project. Okay. So I have to first select which board. Based on my board, I have to select it. So I know mine is a STM32 G4 board, so I click that. And mine is a Nucleo G474RE. This is my Nucleo board. So I click it, and then I will start my project. It says, do I want to initialize all peripherals with the default mode? I'll click yes. So it takes some time actually to open. Okay. So now the board has been opened. If you see, this is your 64 pin microcontroller. Okay. This is the package and 64 pins, etc. are there. And this is, see, if you see over here, this is your B1 blue push button. So the blue push button which I showed, all right, so that is configured to this pin. So there are some peripherals which have been initialized, which I will not be using. So I'm going to disable them. So these I am not using, so I will disable. These I disable them. This I'm not using, so I disable it. Okay, so this meeting will end in 10 minutes. Then I will again start the meeting again. So I've just left the green LED pin as well as the blue push button pin. We are currently not going to use it, but for many of your simple codes, you would like to use this push button and this LED or blinking LED, etc. So that's why I've left these pins initialized, but the other pins I have disabled because I'm not using them. So I'm going to use a timer. So I will go to the high resolution timer, which I'm demonstrating today. So I've selected high resolution timer. High resolution timer is a single timer which has multiple timers are available, A to F, and each timer A can generate 2 signals, timer B can generate 2 signals, etc. So it can generate in total 12 signals. I'm going to use timer A. There's TA1 and TA2 output active. So I want both the outputs of timer A to be shown. So that's why I click TA1 and TA2 outputs active. Now I click TA1 and TA2 outputs active. And if you will observe over here, these 2 pins have been selected. That this pin and this pin has been selected. And these will be used for sending out the output signals of TA1 and TA2. Okay. So TA1 is channel 1, TA2 is channel 2. Now, over here, I will configure the parameters of the timer A. Okay, I will configure the parameters of the timer A. So, there is a clock. If you will observe, if you come back over here, is this visible? There's this clock, okay? There's this clock to your timer, to your counter, okay? So I want to select which clock I want to select. So I'm selecting over here this is the clock. Okay, I am just selecting a clock of 1.7 to into 10 to the power 8 hertz. That is effectively 170 megahertz clock. So I have selected a clock of 170 megahertz. So the clock which is coming over here, the clock is coming at a frequency of 170 megahertz. Now I have to select the TBPRD value. Okay, the TBPRD value. So for my example, okay, over here, I want to select TBPRD, what value I must give it. My clock is 170 megahertz, 170 10 to the power 6. I want a frequency of 20 kilohertz, that is 20 into 10 to the power 3. So I will get this and this gets cancelled. It becomes 17 upon 2, that is 8.5 into 10 to the power 3, that is 8,500. So my TBPRD has to be 8,500. Okay, another thing is I want to compare duty ratio. Suppose I want the duty ratio to, let's say, to be around 40%. Okay, let's say the duty ratio has to be 40%. So we see the formula over here. Duty has to be 40%. So my compare one value will be duty, which is 40%, is 0.4 into TBPRD, that is 8,500. So what is that? Or okay, we'll just keep it
3400.
3400. Okay.
00.
So this is my compare one value. So I will have to use these values. Okay, please remember them. So now I have selected the clock. I have selected a clock of 170 megahertz. Now there is an option for user constants. So these are constant variables which I define their values, and they are constant throughout the code. So I add a constant with constant name TBPRD, the value 8,500. Okay, and I have added it. Then I have added a value CMP1 with the value 3,400, right?
Yes, sir.
Yeah. So CMP1, so these values, these user constants I have defined. Now it is showing the resulting PWM frequency. If you give this value, this is a hex 16-bit, no, this is a FFFXT 16-bit value. It is in hexadecimal format, so it is a 16-bit because of D is 4 bits, F 4 bits, etc. This we had seen earlier. I just give the value TBPRD. If I give the value TBPRD, you will observe it has become 20,000 hertz, so 20 kilohertz. So my resulting PWM frequency is 20 kilohertz. Then there are various parameters. So that is why the CubeMX is useful, because we are initializing these parameters. 1 minute, I'll just save my file. Okay, I'll just save the project. Otherwise, we should not lose this. Open loop PWM. Okay, I will save it. So I've saved this in the folder which I created, open loop PWM. Then these things you can ignore. Up down mode is timer counters operating up counting mode. Up counting mode is like this. Okay, it is counting up counting mode. If it is in up down counting mode, it will operate like this. Okay, this is another type of counter thing which they use for other applications. But in our application, we just use it in a up counting mode. All right. Then, so this is done over here. Faults, dead, etc. Burst mode. These are some advanced stuff. We want to insert a dead time. Okay, and something which is important to us is this is, let us see over here. Okay. Okay. So this is your signal. Okay, this is your signal. But I want two signals. Okay, the next signal will be complementary of this signal, but that complementary signal must have certain dead time. See, the next signal must be something like this. Okay, must be something like this. So this is known as your dead time. Okay, this is your dead time. This is known as your dead time. All right. Because why we want that? We don't, why do we have that? So, no, this would be a MOSFET. So, as you know, this is a gate 1, gate 2, and this is your V bus, assume, and this is your ground. Okay, so the PWM signals will go to the gate driver, and from the gate driver it will come over here, all right, to these two MOSFETs. So these two MOSFETs must be complementary, because if they are not complementary, then this entire thing will be shorted and lots of current will flow. So that's why we must introduce a certain dead time. Okay, we have to introduce a certain amount of dead time, such that when one switch is turning off and another switch is turning on, this switch must completely turn off, then this switch must turn on. So that dead time is necessary to avoid shoot throws. So it should, because it could happen that one switch is just turning off, partially turned off, but the other switch turned on. And so then both switches are on simultaneously, and then there'll be a short circuit. So to avoid that, we introduce a dead time. So I am saying over here that I want, where is it? A dead time insertion. I want a dead time to be inserted between output 1 and output 2. So I insert a dead time between output 1 and output 2. These things you don't need to know. Now I have a compare 1. If you observe, remember there's a compare 1. Okay. So there's a compare unit 1. So it's possible to have 4 compare units, but I'm currently using the first compare unit. So I enable compare unit 1, and the value which I assign to it is CMP1. So I assign it a value CMP1. So what happens is timer compare 1 event is generated when counter is equal. What does it say is when the counter becomes equal to the compare 1 value, then it generates this event. It generates an event. So, okay, so compare 1 value I have assigned. All right, so that basically it is just an event. It's just an event. So when this happens, when it reaches over here, it generates an event. So what will happen on that event, we have not yet decided. We have just configured that when compare 1 value becomes equal to the, when the counter value becomes equal to compare 1 value, then an event is generated. Okay, so an event has been generated. Now we will see how will we use that event. These things are advanced features which you don't need to know. Dead time, how to generate. Yeah. So dead time we will look into it later. First dead time we will see later. First we will see how to generate the output 1. So I have to generate the output 1. If I generate the output 1, my output 2 is complementary of the output 1 with dead time. Okay. So there's a set source. Okay, one is output is active high. Okay, that's fine. Set source. When am I going to make it high? When am I going to make it high? There can be multiple set sources, but I need only one set source and one reset source. So one set source is when the timer period event starts. When this period event starts, that you're able to see my pointer, right? When
Yes,
I need
yes.
one set and one reset. So when this timer period event comes, when it becomes 0, that is when my set must happen. And when it reaches this compare 1 event occurs, then it is my reset. So I go over here. So number set sources, I will select, I need one set source. Okay. Now which source I need? I need a source when timer period event, it forces the output to its active state. Active state means high, 1. So I click this. I click timer period event forces the output to its active state. Next, I need a reset source. So I will select how many reset sources I need. I need only one reset source. So I click it. Then which event? I will select timer compare one event forces the output to its inactive state or to its low state. So I will click this event. Okay. So I click timer period event will force the output to its active state. Timer compare one event forces the output to its inactive state. So I've configured the timer. All right. Then timer output 2 I cannot configure because it is dependent on output 1 and the dead time. Okay. So then over here, I cannot make any changes. Next we will look into dead time. Now I need to generate a dead time which I need to generate. Let us assume this over here. There's this clock is coming. Okay? There's this clock which is coming periodically. All right. So I want to use this clock and I want to generate a dead time. What I want to say is after this clock has come, let us wait for around some amount. Okay. You wait for this much amount and then you generate a complementary signal. So if you see the complementary signal must be something like this. Okay. It must be complementary. All right. So this amount of time which I am going to wait. Okay. This amount of time which I want to wait is my dead time. Okay. This is my dead time. And this dead time is dependent on these clock signals. So suppose I want a dead time of, if you remember, our switching frequency was, PWM frequency was 20 kilohertz. Okay, 20 kilohertz. I want, so it is, its period 20 kilohertz would be 50 microsecond. Okay, it would be 50 microsecond. Is it correct? 20 kilohertz and 50 microsecond?
Yes, sir.
So let us assume I want a dead time of 100 of 1% of that. So that would be around 500 nanosecond. Okay, I want a dead time of 500 nanosecond. If I want a dead time of 500 nanoseconds, then how many clock signals, how many these clock signals I need to wait for it to generate a dead time of 500 nanoseconds. So dead time of 500 nanoseconds into this clock signal, which is coming at a frequency of 170 megahertz. If I do that, then I will get how many such signals, 1, 2, 3, 4, how many such counts I need to wait for my dead time. So can anyone say 500 nanoseconds into 170 megahertz, how much does it come out to be? It actually comes out to be 85. Okay, it comes out to be 85. So I wanted dead time to be inserted of 85 of
Yes,
85 counts.
Yes, sir.
So the dead time which I will insert will be like this. Go here. I will insert a dead time of 85 and my dead time generator, that clock is same as my high resolution timer clock, which is 170 megahertz. Okay, this is for positive dead time on the rising edge, and I also want a positive dead time on the falling edge. So also I give it a value of 85. Okay, I give this also a value of 85. So now I have generated my dead time. Okay, I've also configured this with a dead time available. So now I will.
Sir, we have given.
Tell.
Sir, we are giving dead time for 85 clock cycles, right?
Yeah, 85 clock cycles. Yes.
On both the sides.
Both the sides. So effectively, my total dead time is actually effectively 1 microsecond. Yeah, my total dead time. My total dead time is 1 microsecond because it is 500 nanosecond plus 500 nanosecond, which is 1 microsecond. Yeah.
Okay, 170, we are right.
All right. And actually, this I have not drawn properly. Let me just go over here. It would be something like this. Suppose this was your original PWM signal, okay, which you got without dead time. Then after your rising edge, you wait for 85 clock cycles and you generate this signal, okay, which comes over here and turns off over here. So again over here 85 you wait, and then this signal comes and then this signal goes. But this is your channel A1. Okay, Okay, your channel A2 signal will be after the falling edge, you wait for 85. Okay, you wait for 85. So that is your high. And this is where it goes low. Again, you wait for 85 over here. And this is your high. All right. So this is how
Hello.
the signals are complementary. Yes, yes, tell.
Can you summarize that procedure over STM
Okay.
and GUI? Yeah, total
Oh.
total procedure. Yeah.
Okay. Total procedure is basically first new, like, should I start from the creating the project, everything, that one? Or you're talking basically of the
No,
time?
only timer. Yeah, only timer.
Okay. So I've selected my high resolution timer. Okay. And based on my calculations, I selected what value I must set for the registers for setting the frequency and for the duty ratio. All right. So those values I have put over here. I've added in the user constants. I've added those values. Then
These are only for open loop, right? That is
yeah, this,
CMP1.
yes, this is only for open
Yeah,
loop.
yeah.
For closed
Okay.
loop, it is advanced loop. You'll have to do.
Okay.
So then I have to first select the clock. I have to first select the clock to my input with like this clock. All right. This clock. I have to select this clock. This clock I have to select.
Okay.
So for selecting that clock, I have to select what is the frequency. There are various options over there. It could be 170 into 2. Okay, it could be 3.340 megahertz, etc. All these are available. I'm going with the simple one, 170 megahertz. Then I add the TBPR, the value which will set the frequency, and the frequency is coming, and I can cross check it over here. I have the provision over here. Okay, it is up. Then I want to have dead time. Okay, I want to have dead time. So I click this option. I want to have dead time inserted. Then I will just compare unit one, compare one value I've given to it, and it is generated when the counter is equal. So these are the events. Then my output one, okay, it needs one set source, and that is the timer period event forces the output to its active state, and reset source is timer compare one event forces the output to its low state. Okay, so I've selected output one. What is the logic for generating output one? Then I went to the dead time. I wanted to configure dead time. So based on my calculations, I had to give value 85. I gave it for both the rising value and the falling value 85.
Okay.
Yeah. So this is thing done. So now I have generated it. I configured it. Now I will generate the code. So I click on generate code, and it will be generating my user source code.
Basically, how much percentage of our class cycle that time should be?
See, dead time, it is a very tricky thing. You don't want it to be, you don't want it to be too long, so that it will like
too short.
too short. It is dangerous. Basically, here and all, we give a large value, or if we find that this cross conduction is still happening, then we have to increase the dead time. A trial and error process. There might be some papers on how to actually come up with a good value, but I don't know currently. Right? So I generated code by using it open. Okay. Look, PWM E1. Okay, this is the project.
Sir, that is so positive dead time, right?
Yes. So positive dead time, yeah, positive dead time, yes.
What does it mean, sir? Positive dead time?
Like I drew this, no? After this has happened, after 85, this is your original signal. Okay, this is the signal which comes from comparison. The comparison event, this is your signals which are coming out. Then to generate the signals, you have this channel A1 and channel A2. Okay. So after the rising edge, you wait 85 and then you turn this on. And when this turns off, you immediately turn it off. This is the logic for channel A1. For channel A2, this is a different thing. So after 85, okay, that is why it is positive dead time. If you configure it
So
as
if you give negative,
negative 85, it will come
okay.
like this over here, right? And then it would be there. But then it be
Before.
tricky at the starting instant. It might be tricky on that, but you could try it out. All right. So this is for the dead time. So I've selected, I've generated the code. The code is come over here. All right. I opened EVOM. Now I want to go to main.c file. So I go to application user code main.c file. I go to main.c. All right. So this is my initialized code. All right. All the configurations are there. The handle for the high resolution timer, then initializing the peripherals. Okay. Then the while loop is over here. Then all these are a clock configure that it will generate. So I don't need to be worried about these things. That based on the configuration of the CubeMX, it has generated this code. Similarly, the high resolution timer, it has configured all these sets of codes are there. Okay, so don't get scared. This is generated by your CubeMX. You don't need to worry about these things. Okay, later on after using, you will understand these codes better. Now, I want to write. Now it has generated the code. That doesn't mean the timer will automatically start running, functioning, etc. No, you need to start the timer. You need to set up output waveforms to come. For that, you need to write some certain functions which are already defined, which already predefined functions are there. You have to call those functions and configure them with the correct arguments. So whenever you're writing your own code, you want to add your logic, you must always write it between this user code begin one or user code end one, or either you could write it between user code begin and user code end. So your code which you're writing to this initialized code must be between this begin and this end. You cannot write a code over here. If you write code ABC, something you write, all right? Then what will happen when you're again refreshing this, again reinitializing this, then that will disappear. That will be wiped off. But if you write the code over here, okay, and then when you reinitialize it, when you regenerate the code, etc., then that code will remain. It will not be lost. So whatever code you're writing, you have to write it between user code begin and user code end, right? Then I want to start.
Hello.
Yes, yeah.
Yeah, sorry for the disturbance. Like,
yes.
what is mean by hall and low layer APIs and middleware? What is the difference between?
HAL is like the hardware abstraction layer. Its full form is. It is about the. You don't need to know the exact details of which register is being turned on, which register bit is being set, reset, etc. You don't need to know. It has considered all that happening, and it has written an overall function that does those things internally. So you just call that high level function. You don't go into the bit level and do it.
Register level. Yeah.
The register level. Low level is at the register level. You set which bit, all those things. That is more complicated. Now, when you're starting out, it is advised to go for a use HL functions, and because there are many things you need to first, you need to start one bit, set one bit, and reset this bit. All those things are there. Okay, that is not easy for a beginner to understand and to spend time. You will get lost in it. So there are already used HAL functions are there. You use those HAL functions, and then once you have reached a good, comfortable level of expertise, then you can want to make the code work faster, etc. Then you go to low level libraries. You can go to that. Okay. So that is there. Now I want to write the code for starting my timer. Right. So these are the codes. Where is this? These are my codes. I have written these codes earlier. Right, so I'm just copying it and pasting over here. So I have copied it and pasted between user code begin 2 and user code end 2. So one code is for starting the outputs. Timer A's outputs 1 and 2. It is given by HAL high resolution timer waveform output start, output TA1 and output TA2. Okay, this by plus is like the ORing thing. And this is the handle for the high resolution timer 1. Similarly, then I want to start the high resolution timer counter. I want to start it. So I have called it a timer ID timer A. So these are the codes for starting my timer A. So once I have written these codes, then I can proceed by running the code. So if I first what is advised is to compile your code to check if there are any errors. So I compile my code, it is compiling, and it's showing total number of errors is 0, no warnings. So it is good. Now my code is good. Now what I have to do is I have to connect my microcontroller. My Nucleo board, I will connect it. You guys will not be able to see, but I'm connecting my Nucleo board via the USB cable to my laptop. So it shows that my Nucleo board has got connected. This pop-up comes up. This pop-up is coming. Then I will download and debug. So I'm debugging is like I'm sort of flashing the code from my CPU. It is being dumped into the microcontroller. Right? So it is happening. You can see that these codes are being dumped. Still taking time. All right, and then I will run the program. Okay, I will run the program. So just hold on. I will have to join the meeting so that I can show it. Now is it visible?
For me, it is not.
What about others? Visible for others, like because I can see it on my screen. Maybe you have to change the layout or let me use it. Are you able to see it now?
Now it's visible.
Now it is right. So
Yeah.
this is my Nucleo board. Okay. This is my Nucleo board, and this is where the PWM signals are generated. So this is seen on the oscilloscope, right? And if you see, they are complementary. One is your channel A1 and one is your channel A2. And if you further zoom in, you will observe there's a dead time. You will see that this is visible for you guys. There's a dead time is there. Okay, a dead time is there. Right. And we can also check how much dead time is there. This cursor over here. And if you will see, there's a delta over here. This is a delta over here that is around 496 nanoseconds. And we had set for 500 nanoseconds. Okay, so it's approximately equal. Right? And if you see, now we want to see the entire, we want to see the frequency. Okay. The frequency is what? From here, it is turning on, and here it is turning on again. So this is the entire time period. And the time duration is around 50.2 microseconds. This delta is coming to be 50.2 microseconds. That is your frequency for 20 kilohertz. Right? So are there any queries in this?
Sir, can we see the clock here?
No, clock is not visible actually. Clock is internal.
No, no. Is it? Okay, because we want to see that 85 clock here.
No,
That is not possible.
possible. Okay. So that just by zooming in and you see the dead time which is getting calculated, from that you can see whether it is working as per your calculations. Okay, but we have observed that it is coming correctly. All right. Okay, so I'll stop the video. Okay. So I hope this has been useful for you. All right. So now we can unpause this. So this is for generating PWM. Simple PWM we have generated. Now we have an ADC. You guys can see my screen, right?
Yes.
We have this microcontroller has 5 ADCs, which are successive approximation register ADCs. And these can generate interrupts and they can be triggered by software or hardware, etc. As well as the ADC has certain supply and range. All right. So this is my ADC. This ADC is internally present in the microcontroller and it has a bias supply, B bias. Some supply is there to the ADC, that is 3.3 volt, and it is with respect to a ground. The ADC which I am going to use is configured as a single-ended mode. Single-ended means I require only one pin because the signal which I want to measure, is with respect to ground. Okay, it is with respect to ground, and the signal can range only between 0 to 3.3 volt. Okay, this is the range the signal can span. All right, and this is my digital output. My digital output of my ADC is given over here. Now, it is a 12-bit ADC. Okay, 12-bit ADC. So the value digital value which will range is between 0 to 4095. Okay, 2 raised to 12 minus 1, 0 to 4095. So if I have 0 volt here, it should show me around 0. If I apply 3.3 volt here, it should show me 4095. All right. Any queries in this? Okay. If there are no queries, I'll proceed. So this is one option. Okay, but this is just a number. It is coming 4095. Suppose it was 1.65. It will show me around 2048. Okay, around 2048 some value. So this is not easy for me to interpret some value 2048, some value. It is not easy for me to interpret. So there is an option known as gain compensation. I can do gain compensation. So whatever value it will generate 4095, the ADC will convert that into some particular value based on some formula which is available to us. So I have written it in such a way, if I give 3.3 volt, it should generate 3300. Means it is converting from volt to millivolt. All right. So if I give 1.65, it should show me 1650. Is there any query in this? So the span of the ADC is between 0 to 3.3 volt. In the default configuration, if I give 0 volt, it will show me 0. If I give 3.3 volt, it will show me 4095. But this is confusing, a bit confusing to understand. What I'm doing instead is there's a provision for gain compensation. That means it will convert this value into a value which is easier to understand based on what I define. So I set those values in such a way that 3.3 volt gets converted to 3300, a value of 3300. So basically I'm converting from volt to millivolt. One more thing is required.
3000.
Yes, yes.
This 3300 will be available in
over here.
Digital pin.
Yes, yes. No, digital pin. The ADC is an analog pin and the digital value is internal, stored in some register inside the microcontroller. All right.
Okay.
So instead of storing 4095, it will store instead 3300.
Okay.
So this provision is there.
So it is not in this pin inside the ADC.
This is the pin.
Both this.
This is the microcontroller, and assume this is your microcontroller. Okay. And there's a pin over here. And that pin is connected to the ADC, which is present inside the microcontroller. And this digital thing is internal in the microcontroller. Just not, this digital thing will actually come out like this. There'll be like around 12 bits. Okay, 12 bits will be there. Okay, I've just simplified it by showing only one. So it will be 12 bits are there, and that is stored in a register. Some sort of register will be there. Okay, register. It will be stored in the register. So either it could store 4095 or it could store 3300. Or it's some other value based on the logic or values are different. But I have configured it such that it will, for 3.3 volt, it will store 3300. Okay. This is again
Okay, sir. Can proceed.
compensation. Another thing is my ADC needs a clock, trigger clock. Okay, it needs a trigger clock. Only then it will start sampling. It gets a trigger, it will take the sample, and then it will give trigger a clock, it will take the sample, and then it will give my digital output. Okay, digital data vector. This trigger signal I have to generate. Okay, that trigger signal, how do we generate these trigger signals? That I will show. Okay, this is for gain compensation. These are there. This you can check later. Okay. So this one we have completed for open loop PWM. And this is for open loop PWM. Finish this. I have already configured it. ADC interrupt mode. Okay, the ADC will work in an interrupt mode. So I'm opening those files. Okay. Okay, there's another. Does anyone know what is an interrupt? Can anyone tell me what is an interrupt? Okay, like what do we say when someone interrupts us? Like we're doing something and someone comes and interrupts us and says stop it and do
It's
something.
raising a flag.
Yeah, yeah. So
It's
like that.
raising a flag.
Flag. You're right. So what happens is you have your ADC. Sorry.
Yes, no, some set of codes will be inbuilt, so it will run that code. They call
Something
some
similar.
subroutine.
Yes, interrupt service routine. Okay. So this is my trigger. Okay, my trigger to my ADC. It will take the sample and it will convert it. Okay, but there's a delay. There's a delay for converting my data. Okay, from analog value to digital value, there's a delay. So there's a trigger. This trigger comes over here. Okay, trigger will come repeatedly over here. And like this, trigger signals are coming. But my data, which is coming, this is digital data is shown like this. Okay, so this time for it to get updated, this time it's not to scale, but this time is my delay time. Okay, my delay time, my conversion time. Once it has finished converting over here, it will generate a flag. Okay, it will generate a flag. And I have configured the ADC to generate an interrupt. And when that the flag is raised, then it will go into that interrupt service routine. Will go into your interrupt service routine. So how we will look into how we have configured it. Oof. Okay, so first I will like similar way, two high resolution timer clocks I have generated. High resolution timer PWM I have generated. So that is the same. That you don't need to. That we'll see what we use that for. It generates a PWM signal. That is fine. Now I wanted to generate a trigger signal, okay, to generate the clock signal, to generate this clock signal also to my ADC, I need an event. So that event I generate from my timer. So earlier we used compare unit 1 for generating my PWM logic. Okay. Now I can use compare unit 3. There are only some particular compare units which I can use, and I have found out from certain examples or that I can use compare unit 3. In compare unit 3, I will store a value ADC underscore trigger. Okay, ADC underscore trigger is again another value. So let me just, this is my counter. Okay, this is my counter. It is proceeding as follows. This is my compare. Suppose this is my ADC trigger, and this is my compare one value. Assume. So it will generate the duty cycle like this. Okay, it will generate the duty cycle. PWM signal, it will generate like this. Okay, that will go on. But at this instant, it will generate an event. At this instant, one event has occurred. And this event, which has occurred at this instant, this event is basically my trigger clock. This event is basically my trigger clock. All right. So using my timer, high resolution timer, I am generating an event which I'm using to trigger my ADC. All right. So over here, I have generated an event. ADC underscore trigger is the compare value. Once the counter reaches that compare value, it will generate an event is generated. Now, there's an option known as ADC trigger configuration. So I click on ADC trigger configuration. Then I'll enable ADC trigger 1. Source is timer A. And ADC trigger on timer A compare 3 event. So when timer A compare 3 event happens, then an ADC trigger 1 signal is generated. Okay, an ADC trigger 1 signal is generated. So till now, I have spoken on how to generate a trigger signal for your ADC. So using a high resolution timer, I am generating a trigger signal for the ADC so that I have prepared that signal. That signal I have made. Now I want to go to my ADC. Now I want to configure my ADC. So I go to ADC 1. Okay, I'm using ADC 1. There are various channels of the ADC. So the ADC which you have doesn't have a single pin. It can have multiple pins, multiple inputs it can have, and each input can be selected one at a time, etc. Those things are advanced stuff. I am just selecting input 2. I have selected input 2 in single-ended mode because I'll require only one pin. Okay, ADC input 2 is single-ended mode, which is only one pin. Now, I will configure it, that is asynchronous clock mode divided by 4, etc. 12-bit resolution. Gain compensation. I have the slide is there. I didn't show you much about it, but gain compensation option is there. Okay, gain compensation option is there, and I have used that. Now, I have now this is for my ADC trigger. See, ADC regular conversion mode. Okay, number of conversions is 1. Which is a trigger source. So high resolution timer trigger 1 event. That event I generated earlier. Okay, that event I generated earlier. So that event I have selected. Then trigger detected on the rising edge. So when that event happens, when the edge is high, rising that time. Okay, so in this way, I have configured the ADC to be triggered by the high resolution timer, and I will also configure the ADC to have gain compensation. All right, gain compensation. There are other things I have left it as it is. I have not made changes to the other things. They are left as it is. All right. So now I have configured the ADC according. So now I have configured the ADC, etc. Now I will go to my code. In the code, I'll open my code. So this is my code. All right. I have told that some variable ADC underscore val. Okay, this will store the value of the ADC. and it is unsigned integer of 16. So 16-bit unsigned integer. ADC underscore val is the value. Okay, this you ignore for the time being. Then in my user code begin to, I have started the high resolution timer because I'm using the high resolution timer. I've started it. Then I've done ADC calibration. Okay, this is the code for calibrating my ADC, and this is my code for starting the ADC in interrupt mode. So I've written these codes. Okay, written these functions I've written. All right, DAC I'm not showing right now for you guys. So the ADC I'm just calibrated, and then the ADC is started. And in case there is an error, it will go into the error handler. This is just an additional, safety feature, etc. But it is usually doesn't throw an error. So now the ADC is started and ADC is calibrated and the ADC is started in interrupt mode. Now I have also one more thing I forgot to tell over here. The NVIC settings, that is the interrupt, have been enabled for the ADC1 and ADC2. So I've enabled these interrupts for ADC1 and ADC2. Now, in my code over here, these are codes for configuring the ADC, configuring the DAC, configuring the high resolution timer, etc. You can ignore this. Don't delete it. You require it, but you can ignore it. Now, there's a function, HAL ADC conversion complete callback. So when my ADC is finished conversion, the interrupt is generated and it will go into this function. All right. In this function, what I have defined it to do, that is your interrupt service routine, which you had mentioned. It will check if it is coming from my ADC1. It will check if it is coming from my ADC1. If there are multiple ADCs, then you need to check from which ADC it is coming. Okay. Now I've checked. It is coming from my ADC1. Then there's a function HAL ADC get value. Okay, it will find the value of my ADC. Okay, it will find the value of my ADC. It will take it. Okay, this for the DAG you can ignore for the DAG. I'm not showing it right now. So the value of the ADC is stored. Okay, so this is my code, and now I will run it. Okay, I will run it. First, I have to connect my microcontroller. So I've dumped the code into my microcontroller. Now I'm going to run the code. Okay, I'm going to run the code in the microcontroller. And if you'll observe, okay, so the value is stored in this. This is ADC underscore val. This will store my value from the ADC. Okay, so if I want to view it, I have to go to view. I go to live watch, and there's a ADC underscore val is there. What value is currently shown in the ADC that it will show. It is showing some 6, 7, 14. So this is millivolt. Okay, I've not connected anything to my ADC, so that's why it is showing these small values. Now, what I will do is, okay. So another thing which I forgot to show, this is my ADC1 input 2. Okay, this is connected at PA1. So how will I know where PA1 is connected in my board? So I will go to my user manual. I will check where is PA1. It shows that PA1 is in my CN7 connector and at pin 30. Okay, CN7 connector at pin 30. So I will go to that. I'm doing it on my board. Okay, if you see the value of what I've done is at CN7 pin 30, which is connected to the ADC pin, I have connected that to 3.3 volt. All right, let me just show over here. If you can you see the microcontroller? Is it visible?
No, sir. The second screen, your face is.
So my face, okay. Let me reverse it. Has it got reversed?
No, sir. It is
Not
not
at all.
reversed.
Not it got reversed. Now?
Yeah.
I'm not able to see that.
Yeah, now it is reversed, sir.
Is visible, right? One minute. I'm not able to
Ah,
see.
yes.
Just a minute. Just a minute. Okay, so this is my microcontroller. Okay, so this is my CN7 pin 30. Okay, I connected my female pin. Okay, this is my female pin. Okay, this 38, 36, 34, 32, 30. I connected to pin 30. This is my input to my ADC. I connected this pin. All right. Then there's something, if you will see over here carefully, there's a 3v3 written. Okay, it is not seen for you guys, but there's a 3v thread 3. Okay. 1 minute. So this 3v3 pin is connected to 3.3 volt and I connected. So I'm effectively connecting my ADC to 3.3 volt. Okay. When I connected to 3.3 volt, what am I seeing over here? I am seeing a value of
3299.
3299, which is approximately 3300. Okay. So because I use gain compensation. Now what I will do is, and then when I connect this back to 0, okay, there's a ground pin. I connect it to ground. It will show a value of 0. Okay. If you see, it is showing a value of 0. Now, what I do is I remove gain compensation. I go to my ADC. I'll remove gain compensation. I give it a default value 0.
Sir?
Yes.
Sir, here we have connected the pin number 30 of CN7 and then pin 3v3, right?
2 3v3 pin. Okay, there's an Arduino connector, there's one 3v3 pin. So I connected there. So in that Arduino connector, the 3v3 is also there, 0 is also there, ground also there. So I connected that. Now what I did, I made a change. I made my gain compensation. I have made the change and I've again generated the code. So the change which I have made, because I made a change, I'm generating the code all over again. And over here, I must click yes to all. Changes which I've made, I want it to be updated. So I put yes to all. If I do that, this session will stop. Okay, this whole thing will stop. I have to all over again. I have to redump the code. Okay, so all over again, I'm going to redump my code. I'm going to dump my code. Okay, so just let it be like this. If I'm dumping my code, in the meanwhile, if you'll observe, this is my microcontroller. It is getting power from the USB. Okay, and this is my push button, and this is my reset button, and these are my signals for my PWM that is connected over here. Okay, so these also I have checked from the user manual, and I found out which pin has to be connected to what. And these things are taken by my probes. Okay, these probes are connected to my oscilloscope. Right, so these probes are connected to my oscilloscope. Okay, so I'll come back over here. Okay. Now again, the live watch is there. Okay, I will run it. The value it is showing is 0 because it is connected to ground. Now I will remove from the ground and I will connect it to 3v3. Okay, when I connect it to 3v3, the value it is showing will be 4095. So in the same way I've shown, like using gain compensation, it comes out to be 3300. I configured it in that way, and if I don't use gain compensation, it gives the value 4095. All right. Okay, so I'll stop this. So in this manner, we were able to see
that this 40 comes from that register. Sir.
Yeah, it was stored in that register. Okay, because the input to my ADC was 3.3, so it gives the value 4095. All right. So let me cross this off. All right. So that we studied about the ADC peripheral. Now we can see about the DAC peripheral. Okay. Now we will see the example code. There is an example code already available. So there's an example code. So when you download STM32CubeMX, then you can go, these things will be stored in the repository. So what I will go do is, I will, in the repository, I go to the G4, okay, STM32Cube G4, because it is Nucleo G474RE, so G4 it is. So I go to this, then in my projects, Nucleo G474RE is my board. Then in the examples, I am going to show you for the example for DAC. Okay, so I go to DAC. Then DAC signal generation 2. And in that, I open my EVARM. Okay, my EVARM I open and I open this project. Now, this is my example code which is already available. But to understand it, there's a README document. Okay, there's a README document. In this document, it is telling what happens. Okay, there's an internal DAC wave generator. It is used to generate a sawtooth wave. Okay, there's also a user push button. Now, which signal is generated depends, can be changed. It can either be a sawtooth waveform or it could be a sine waveform. And for sine waveform, they're using some DMA concept. So that is secondary. So basically what I want to demonstrate is using the DAC, we can generate a sawtooth waveform as well as a sine waveform. And there are codes which are which this example has provided to us, which we don't need to know. Okay, it has provided. We can look at those codes and you can use that code to write a similar code for creating your own wave, etc. All right. So now this is my code. This is the code. I will go to my main.c and I will run this code. So I'm running the code.
We have to.
Sorry.
Sir, for seeing this sawtooth or sine waveform, now we have to connect our DSO to the pin number 32, right?
Yes.
The
Pin
last
number
read
32.
is.
Yes. So I will connect it to pin 32. So video is visible now?
Yes, sir.
Okay. So I will do is I don't want to see my timer. I just want to see my DAC. So when DAC is connected to CN7 pin 32, 38, 36, 34, 32. It's connected to pin 32. Now I run it. So if you, I've run it, and if you see, this is my waveform on the oscilloscope. It's showing my, it's not properly triggered, but you can see it is showing a sawtooth waveform. It is showing. Okay, and it is approximately 3 volt. Approximately it is 3 volt. You might even see it reading. Okay, this is my oscilloscope, and a sawtooth waveform is being generated. Now what I will do is I will click my user push button. So I go and click my user push button, and if you notice, it has become a sine wave. If I click it back, stop. This is how it is
The
operating.
recording is glowing.
Is it, you're able to see?
Visible, sir. Now it is correct, sir.
This is my DAC. Okay, this is my ramp sort of wave. Now I click it, it becomes a sine wave. The problem here, it is not properly triggered. That's why I was using single shot mode. So now it is clear. Okay, this is my sine wave. Okay. Now I again click it, it becomes a what do you say? A sawtooth wave. So in this manner, you can use your microcontroller and you can refer to these examples and you can, what you say, write
Sir,
your own
here
code.
we have down.
Yes, Ted. Hello.
Sir, the thing is, here
Mhm.
before, sir, is there a requirement like only after connecting the pin 32 to the DSO, we have to burn this program into the
No. There's no requirement.
microcontroller?
No requirement like that. There's no requirement. You see, in a normal application, you first burn the code into microcontroller, then you use it, right? So there's no requirement that your pin has to be connected first itself. Okay. All right. So that is for the DAC, DAC. Similarly, it also has its CubeMX file is available, etc. So this is an example for DAC. Yes.
No, sir. For learning this STM32, I think this board and DSO on our PC is sufficient, right, sir?
Yeah, it is sufficient.
Okay.
And this is like very cost effective. Like, say, if you have a DSO and you have a laptop, then you just have to procure your microcontroller, this Nucleo board, and this comes within 2000. Okay, and you can generate the PWM signals, you can run closed loop, etc. You can do it with this. See, now if you want an FPGA, you have to buy the FPGA kit. You have to then ADC, DAC also, you have to make a board, signal conditioning board, and those you have to interface it to your FPGA. All that headache you have to do. But over here, we are using the internal ADCs, internal DACs, etc. You can use to run it. Okay, so this is a more effective thing. It's a useful thing which you can do.
Sir, I have a doubt, sir. Actually, nowadays there are some people are talking about that hardware in loop, right, sir?
Okay, yeah, hardware in loop, yes.
Actually, sir,
okay. Yes.
Sir, they are saying some power circuit can be in our simulation, and then we can control using this board.
Okay.
And then we can fire that MOSFET in the simulation using this PWM signal.
Okay, yes. So basically, what they have, what I have understood is, let us consider hardware in loop. Okay, you have your sent signals. Okay, your sent signals, etc., comes to your digital platform. Okay, digital platform, and in the digital platform, you have a model. You have a model of your converter. Okay, you have a model of your converter. Using that model of your converter, you're generating the PWM signals. Okay, you're generating the PWM signals. This I will consider to be hardware in the loop, I think. I am not exactly certain of this, but
Sir, what I try to ask is, sir, suppose we are not having the power circuit here, board of the power circuit here.
Okay.
So if we have a power circuit in a MATLAB like thing, can we?
Okay, to test your algorithm,
can we
right?
test?
I have not used that actually. For STM, I have not. not been able to find proper thing, and actually I haven't searched much also whether it is possible, etc. You could check online whether the STM32 code you can dump it into MATLAB and check in your simulations. That way. Texas Instruments is, I think their provision is there for that. But again, I haven't used that, so I can't say.
So, okay, so actually we can sense that from the simulation, and then we can bring it to the microcontroller, and we can process here, and then again we can feed the PWM from the microcontroller into the simulation. Is that can be done, sir? Is it possible nowadays? I don't know.
Yeah, even I can't comment actually because I haven't
Okay.
used it, so I don't exactly
Okay.
know that way.
Okay, sir.
Okay, so similarly, like for digital voltage mode control, the architecture, right? We have an ADC, and this is the RAM counter. All these you can implement it in the microcontroller using the timer and the ADC. Okay. Similarly, for mixed signal current mode control, let me just okay, you have to use ADC, you have to use DAC, and you have to use the. This is basically like a PWM counter, like a timer you have to use. So using a timer, using a DAC and ADC, these are the peripherals you require. Also, you require a comparator. Okay, you also require a comparator. So all these are inbuilt. They are available in your microcontroller, so you can use it and do peak current mode control. And there's a very nice document which STM has provided to understand peak current mode control. And I had actually added this document in one of the earlier videos. I had added the link to that document also. If you want, I can add this link again over here also. Okay. So,
sir, I don't think it is accessible. I can add again, sir.
okay, that just keep a reminder. Okay. So the document I have to add it. Okay, I'll add this document. I'll add. So one more thing. So there's some learning resources. I have included the links for that. So these are what I have referred to. Getting started with the STM32 and Nucleo board. This is in correspondence with DigiKey, and there's an instructor, Sean Hyman. He instructs how he will show how PWM is generated, what are the various things are there. So that way I found it to be useful. Even Mitch's guide to STM32, this is another YouTube playlist is there. You can refer to this. Then these are some important documents which I refer to. One is the reference manual, okay, about the STM32 G4 series. Then this is for the Hall low layer drivers. Manual is provided. Okay, how to configure the peripheral and what are the various functions which are there, what functions we need to call, etc. Those are provided. The data sheet of STM32G4. For the Nucleo board, the user manual, which I was referring to, which pin connection I need. Similarly, I'm using the high resolution timer cookbook, and there are various examples in this cookbook. There are various examples are there on how can I use the high resolution timer, how those compare values are used to generate various events, etc. So that cookbook also is available. So these are like very good resources are available for you to learn STM32 microcontroller. Okay. So are there any doubts still here?
Can we use? Sir, whether can we purchase it this board directly from STM website, or is there any other?
No. DigiKey is there. Element 14, Robu, From there you can purchase it. And actually I saw in IIT campus also, actually I saw in one of the shops also it was there, electronic shops, this STM32 Nucleo boards. So you can purchase it.
So much access.
It is. I was searching today, but this Nucleo G474RE I wasn't able to find. But there are other Nucleo boards are available, so you could see accordingly and you can check. Okay. So those are the, like, the Nucleo boards are the, will have a different microcontroller, perhaps a different number of ADCs, slightly different number of clock frequency, all those things. But it's like basic same functionality is there. Okay, so you don't need to worry. But that you didn't get this exact Nucleo board. There are other Nucleo boards also are there which you could use it. Just see like how many peripherals are available, etc. But I guess the usual and standard Nucleo boards will have a good deal of peripherals will be there. So in this week, the LLC converter also is taught. So I'll quickly go through the LLC converter. Okay. So the LLC converter is used in electric vehicle battery chargers, and it has various advantages. And it is a primary side full bridge is there, and secondary side it could be a diode bridge or it could be a secondary side full bridge is there. This is used for synchronous rectification to improve the efficiency. And this is diode bridge is simpler to use, but it would be a bit lossy. And it basically uses there is a transformer over here. This is my transformer. And there's also a resonant, there's also an inductor which is there. And there's a resonant capacitor which is there. And these form a tank, LLC tank. Okay. And here, basically, the focus is on getting ZVS switching. So in ZVS switching, of course, the losses are less. And that is why LLC converter is very popular. And it is a DC-DC converter. It's a DC-DC converter. And it is used in electric vehicle battery chargers. These are some gain curves of how the gain varies with the quality factor. So the quality factor decides how the inductor you must choose, capacitor values, etc. And this is your resonant frequency. Okay, this is your resonant frequency. You must not operate to the left of it, you must operate to the right of it. All right. And it is best. And there's a certain range of frequencies for which you can use, and you must not deviate a lot from the resonant frequency. Otherwise, the advantages of LLC converter you will lose that. So based on your, so in LLC, it is pulse frequency modulation. What are you doing is you're changing the frequency. And how are you changing the frequency? You're using a voltage controlled oscillator you're using to change the frequency. And based on the particular frequency, your gain, this is your gain curve. Your V output by V in is a function of your PWM frequency. It's a function of your switching frequency. Okay, it's a function of your switching frequency. And that is determined by the gain curve. Right? So this is an example of a light electric vehicle battery charger. You can see there's a fan over here. This is the fan. This is the heat sink. Okay, this is your fan. This is your inductor is there, etc. This is considered a PFC and LLC. All right. So these are some things, some boards are there. It uses analog plus digital control, etc. What is, they have an analog IC, okay? They have an IC, analog IC, which can be used to, which is used for generating the pulses for your LLC, okay? This is your IC, which is used to generating pulses for LLC. But if I want to change the output voltage, if I want to change this V output, if I want to change, what I require to do is this reference voltage to this controller has to be changed. And to change that reference voltage, I will use the microcontroller. So what happens is the microcontroller has a PWM signal. Okay. Suppose it has a duty ratio of 0.1, then your U out, let us say, would be like around 2 volt. Okay. If the duty ratio is made 0.2, your U out might become 2.2 volt, etc. That relation and all, I don't know how linear exactly, but we'll have to see it. But what is the thing is, you have a PWM signal. Okay, you have a PWM signal. That once, okay, that's the wrong place to draw. Suppose let us say you have a PWM signal. That passes through a low pass filter. Your RC over here, that basically acts as a low pass filter, and it will effectively generate a voltage which has a very negligible ripple. Okay, negligible ripple. Those values must be selected accordingly. So using this, now if I change this duty ratio to be some other value, if I change the duty ratio to be this much, okay, then the DC value will change accordingly. So that is how I vary my reference voltage to my LLC converter. Next, this is another configuration in which they can increase the output voltage range by either using this MOSFET or this MOSFET. Okay, that enables them to span a higher range of output voltage while making sure that the switching frequency does not vary much. This is the board which uses that logic. Okay, now I will just quickly run through C2000 microcontroller. So we spent a lot of time talking about the STM32 microcontroller. We did various examples of the timer, ADC, DAC, etc. Now we will look into the C2000 microcontroller, which is there. It is another microcontroller. It also has ADCs. It also has DACs. It also has these various comparators, etc. The communication, all that is available. And it can also implement floating point logic, and there are various other functionalities of the C2000 microcontroller. So it has a ADC. Okay, this is my ADCs. It also is like SAR ADCs are there, and like also over here post processing, okay, which is also there in the STM32 microcontroller. All these are available. Then there are various things. PWMs, okay. PWMs also can be generated using timers. They also have a very low resolution, which we will look into later. And also these comparators also available, DACs also are available. So many possibilities are available for your C2000 microcontroller. Okay, there are analog comparators, etc., PWMs, and they can be also triggered for fault protection, etc., can be done. Now for EV charging. If you see, this is EV charging. Okay? You have a AC-DC power factor correction, and then you have a DC-DC stage. So the AC signal gets converted to DC, and the DC is passed to DC-DC, which goes to a vehicle, and this vehicle has your battery. Okay. Now there's a focus on bidirectional energy flow. That is, the power can flow from here and here. This is known as your charging your battery. And it can also flow like this from here to here to here. This is it delivering power back to grid. Okay, it is delivering power back to the grid. Power is going back to your grid. So these all are possible, and this is like an area in which research is going on. Okay. Similarly, okay. So like that, there are various topologies for the AC-DC. You can have a Vienna PFC, which is shown here. You can have a totem pole PFC, flying capacitor 3-level, etc. These are possible for the AC-DC converter stage. For DC-DC, like we have the normal LLC can be used, or we can use a CLLC. We can use a dual active bridge converter. We can use all these reference designs are available. These all reference designs are available for you, which you can use. So this reference design has the schematic, it has the layout, it has the bill of materials, it has the how did we design the inductor, how did we choose the capacitor, which and all How did we select the gate driver? Which switches are selected? What is the logic? Everything is available. Correct. So you can use that to understand what is the logic, what is the implementation, what are the components, etc. And you can use that for your research. Similarly, solar inverter also is available. How we have a solar array, then you have a DC-DC converter, which provides maximum power point tracking. Then there's a DC bus. Then we can have a DC to AC inverter, which could be one phase or three phase grid. This DC can be converted to bidirectional DC-DC to charge a battery energy storage system, etc. So this is very like a sort of microgrid application. Okay. So this is there. So for controlling all this, they're saying we can use a C2000 microcontroller. All right. So these are again certain topologies are available. And see why what is happening is we want to have high efficiency, fast transient response, high power density. Also, we want a smaller form factor. Smaller form factor means we want the power density to be very high. We want to have compact chargers, compact converters, etc. Also, the transient response should be good. And for that, we need to have fast control loop. Okay, we should implement very fast. The delay, the lag, these are very critical. They should be reduced as much as possible. So for that, you need an ADC which will update fast. Okay, the PWM should be flexible. It should be reconfigured quickly, and it also for fault happens immediately, you must switch it off. What are the logic? All that is possible using the microcontroller. Okay, pulse width modulator is there, ADC block is there, configurable logic block also is available, like which is similar to how an FPGA. An FPGA is made up of, as we told in the first lecture, it is made up of a lot of logic blocks, okay, configurable logic blocks, which can be interconnected, etc. So similarly, in the TI microcontroller, in certain microcontrollers, this functionality is there. Okay, the various features of the PWM for this TI microcontroller, which you could look into it. So the resolution. Where's my pointer? Okay. Over here, these things, the change, okay, that you want to have the small change. As I told, we were using a clock of 170 megahertz. Okay, if you remember, for the dead time. For dead time, I was using a clock of 170 megahertz. Similarly, and if this clock is made more faster, then I can get a very finer resolution. Very much accurate resolution is possible. Okay, more accurate and fine resolution. So similarly over here, they have a resolution of 150 picosecond is available for the TI microcontroller. Okay. I will again. So this is another basic block diagram. We have a reference voltage. Okay. You have your power stage. Okay. Consider power stage. It generates an output voltage, which you sense it via an ADC. Okay. That gets converted into a set of digital numbers that you can compare with the reference. You generate an error. The error signal passes through your controller. Okay. That generates some value, which is used to actuate your PWM generator and generate this PWM signal to run your power stage. So this is like a closed loop. Basically, you got a closed loop. So how ADCs are there? It could be 12-bit or 16-bit. Okay, how many channels are there to the ADC? All these are given. Okay, like this is the 3.5 mega samples per second. It's a very high frequency ADC, etc. is given here. Okay. Similarly, you can have a configurable this logic block, okay, which can be used. So that is present inside your microcontroller itself for C2000 microcontroller. So those things also can help to reduce space in our system. And these configurable logic blocks are also interconnected. These things are there. Now we will go through a TIDM 02008 reference design. So this is a totem pole PFC reference design. Three-phase interleaved totem pole PFC reference design. So we have one inductor, two inductor, three inductor. So these are the three phases. Remember, this is a single phase totem pole PFC, but there are three, what you could say, three channels or um, three legs. No, let us say three channels. Okay. So the supply, it has a single phase AC supply, but there are three other legs. Okay, three legs are there, and they are phase shifted by 120 degree to reduce the overall input current ripple, etc. So this is the standard topology which is being used, and it has various advantages. It is bidirectional, so it could operate as a power factor correction, that is a rectifier, or it could operate as an inverter as well. So this is your yes.
Sir, it's actually a leg, our usual configuration, right? Then why it is called a totem pole here, sir?
Nice question. I had actually read something because of how a totem pole looks, etc., but I was not convinced with that answer actually. So I'm not exactly sure that way.
Yes, sir, I tried to study this before, but I am not clear with that. That's
Yeah.
this totem pole term.
Yeah.
Okay.
Even I read it, but I didn't understand what it meant, so I left it that way. Okay. So
Okay.
these are your high frequency. These are your high frequency GAN bridges. Okay. So like that, you see, these are all implemented by a daughter card. Okay, there's a daughter card are available. So there's a standard motherboard. Okay, there's a standard motherboard. On that, on top of that, we have this is one daughter card, two daughter cards, three daughter cards, four daughter cards, etc. So what happens when these daughter cards you add, it will improve. Your board is more compact. Okay, but this is for a high level, at a very advanced level thing. It's not recommended that you start at this. So if you see these,
Sir, even,
yes,
sir, which is these are control cards, right?
no, this is your control card. Okay, this is your control card which has your microcontroller. Right.
Okay.
These
What is the daughter
this
card, sir?
daughter card, this high frequency GAN bridge, it is like
Oh,
plugged into your motherboard. It is not present on the, see, this is a horizontal thing. On top of it, we are adding some sort of daughter card. This one. Okay. Here are
daughter
the
card is
switch.
heat sink, sir.
No. The heat sinks are there, and there's a switches also are connected to the heat sink. Okay.
Okay. Then this term I'm newly hearing, daughter card.
Okay. You can check it. So
Okay, sir. Okay.
that's there.
You can proceed.
Then these are the inductors. Okay, these are the inductors. These inductors are there. These are your capacitors. This is your AC input filter, etc. And this is your indirect circuit and relay on this. So this is the actual board. All right. Then it is a 3.3 kilowatt, such a high power just possible. And we try to reduce the TIDM, high efficiency, etc. This can be used for electric vehicles, for telecom rectifier, and for energy storage system, etc. Why? It has high efficiency, and it also is bidirectional. This is one of the main reasons why it is so popular. It is bidirectional. These are the specifications of it, and how you have to sense these inductor currents have to be sensed. Your line current has to be sensed. Your output voltage has to be sensed. Okay, your input AC voltage has to be sensed. All these sense signals have to go to your microcontroller, and then a microcontroller will generate a PWM signals to run these switches, these GAN switches, and this slow MOSFET switches. Then you can also do a trip. You can also use it to generate a trip signal to stop the PWM signal in case there's an overcurrent. And this is the entire control block diagram. This is your voltage loop. This is your current loop. And this is your power stage. And then all these signals are going. The send signal from here goes to your ADC, and accordingly they go into these things. So there's a notch filter is there. There's a PI controller is there. That generates your reference current. That reference current is compared to the actual current. Then there's a PI controller. There are various other things, feed forward, other control techniques are implemented. That generates your PWM signal, and that drives all your switches. Okay, so this is your control block diagram. And then you can also, there's something known as SFRA, the frequency response analyzer, which it can, when the model is running, it can generate, when your converter is running, it can generate the Bode plot of that based on certain settings which you have to do. Okay, so how your model and your measured one, which you measure in real time, or you actually measure when the converter is running, how closely they match also has been shown over here. And this you require for your controller design. Okay, your controller design, which we have studied in the previous weeks. Okay, how from the Bode plot, how we set the, the gain margin, phase margin, the bandwidth, all these concepts come over here. Okay. These are certain test results. Yes.
So this Blu-ray plot can be seen in where, sir?
That actually, the one you could, for this TI microcontroller, they offer two things. You could either see it on the tool as a GUI tool, or you could download that data in a CSV file, and from that CSV file you can plot this. Okay, and from that CSV file you can use it for designing your controller, etc.
So this data we can get from the microcontroller itself.
Yes. Microcontroller. I haven't used it, but this feature is available by TI. And this is some test result. What happens in startup? Okay, how the load is increasing, how the current looks like, how the bus voltage is increasing. Then this is your, this is your input voltage, AC input voltage. How your input current also has to follow that, so that your power factor will be unity. Okay, and the problem with single phase is the DC output voltage will have a second harmonic will be present over here. Okay, so this waveforms are shown. These are test results. Then there's something known as AC drop test. What happens if your supply is lost? Your supply is lost, then your supply comes back all over again. But your synchronization will take a lot of time because of the phase lock loop. Take some time to lock into the input frequency. Instead, these people have created a provision that when your line cycle drops out, still your microcontroller is generating a AC signal wave. Okay, and then it is using that to generate your current reference. Your IREF is generated using this signal. And after some time, when the phase lock loop is synchronized, then you use that for your generating your current reference. Okay, so this is an AC drop test. This advanced feature is there, and these are the actual hardware results. Okay, hardware result is there. How the input voltage drops over here. Okay, input voltage drops over here to 0, and then your inductor current also, input current also becomes 0 over here, and it is off for so long. But that time your output voltage will be discharging, and then when your voltage comes back again, how there's not much overshoot in your current, and it is again synchronized quite well, is shown. Okay, so this is one feature which was there, which they had shown, right? Yeah, so that is all for today. So do you have any queries?
Sir.
Hmm?
No, sir, we can move.
Okay. Yeah. Okay, so thank you for joining. Good night.
Right, sir.
Yeah, bye.